Greetings and welcome, friends. Mr. Waddy and my algebra buddies here, going over solving systems of equations by graphing, graphing, that's right. And solving a system of equations is finding a particular XY combination that will make not one, but both equations true at the same time. So, for instance, if I'm suspicious of whether or not 2, 6 is a solution of the system, I would be plugging 2, 6 in for the x and the y in each equation to determine whether or not they are true. So let's do that. So is 2 plus 6 equal to 8? Is 8 equal to 8? Yes, the audience agrees it is true for this equation. Now question, how many points are on a line? How many points are on a line? The answer is infinitely many points, okay? So I have found one of infinitely many points that work on this first equation, but that does not necessarily mean it also works on the second equation. There's only going to be one point that works on both of those. So I've still got to make sure it works in the other equation. So here we go, is 3 times 2, not plus, minus y, so that's minus 6. Is that equal to 0? That's what I'm trying to determine with these, right? I'm doing checks. So 3 times 2 is 6. 6 minus 6, is that 0? Yes. 0 equals 0. Because it worked in both of these, that means it works in the system, okay? So it is a solution to the system. A solution to the system. All right, you guys agree? See how that works? All right, so that's to check a point. The rest of this was about graphing. Okay, so use the graph to solve the system of linear equations. Check your solution. Neither of these equations are in slope-intercept form, but they already graphed them for us. Maybe they found the x and y intercepts and connected the dots, something like that. But let's see what we've got here. So if I want to find the solution, like I said, there's infinitely many points on this line, infinitely many on that line, but there's only one location where they seem to have something in common. So what is the ordered pair? 1, -3. Thank you, studio audience. 1, -3 is the solution. For sake of time, I'm going to skip the check your solution part. I would just plug those into the values of x and y. But the idea of solving by graphing, I'm going to graph both equations on the same grid and find their intersection. Okay, so here we go. Next problem. Now we're getting into the meat of this. Okay, so here's two equations. I tried to choose the trickier of the problems from last night. Both of these are conveniently in slope-intercept form, y equals mx plus b. So let's figure out what is the slope of this line. I like it. And what is the slope? Oh man, you're so quick. What? You guys agree? We found those slopes. The slope, when it's in slope-intercept form, is the coefficient, the number in front of the x. The y-intercept here, b1, is 2. And B2 is 5. So let's graph both of these lines. So I'll call this like line 1 or something. So it has a y-intercept at 2, so I start at 2, and a slope of 3. So up 1 over 3, up 1 over 3, etc. Let's see, can I access my ruler tool? Waddy fans, I'm getting used to a new writing tablet today, so it's a little slower, a little less accurate, but that's okay. So here's line 1. Let's graph line 2 on the same one. So y-intercept is 5, right? Begin at the B, and then move by the M. So that's up 2 over 3, up 2 over 3. And that's, wait a minute, that's getting further away. Oh no! Are they going to intersect? Yes, they are. Yeah, they'll intersect somewhere over here. So -2 over -3 is the same as +2 over +3. So I can also go down to backwards 3, down to backwards 3, down to backwards 3, and oh, I see that direct hit there. Fortunately, the solution is happening to land on the lattice point, right on that grid. So graphing works fine in these contexts when my solution is close to the origin, right? When it's close to where the axes cross, and it works well when the solution happens to be right on the grid. But if it landed somewhere between there and the answer was like negative 9.72, comma, negative 1.3, it's not going to give me the most exact answer every time, right? So the actual solution here appears to be negative 9, comma, negative 1, right? So negative 9, comma, negative 1 is my solution. I also could think about that as x equals negative 9, y equals negative 1. So that is the combination of x and y that makes both of these equations true at the same time. Let's see. Well, I've got this, I can't. Let's see. Let me open up some Desmos calculator here. And we'll just do a quick check on this. Whoop. Ooh, there's y equals 1/3 x plus 2. Come on. Alt-tab in here. Y equals 1 divided by 3 x plus 2. There's one line. Y equals 2/3 x plus 5. Y equals 2 divided by 3 x plus 5. There we go. Notice Desmos graphs that. You can even click and it will give you the intersection between those, so I can see the solution. Also, in case you haven't noticed, Desmos can also give you your intercepts as well. Okay? So let's look at this next problem. Oh man, this is where solving by graphing would be a pain. By the way, if I wanted to avoid decimals, I could actually multiply both sides by 10 here. This is the same as 2x plus 4y equals 40. And if I multiply both sides by 10 here, that's the same as negative 6x plus 6y equals negative 30. So if you wanted to avoid decimals, as long as they weren't infinitely long decimals, right, you can actually just multiply both sides by 10 or 100 or 1,000 to shift that decimal place. So, friendly friends, even if I didn't convert that to this form, I'm using a graphing calculator. Desmos, hey, you're a graphing calculator. 0.2x, 0.4y. Let's graph using Desmos. Actually, we'll even do it in different colors. So 0.2x plus 0.4y equals, was it positive 4? Positive 4. There we go. So there's one line. Negative 0.6x plus 0.6 y equals, what was it, negative 3? Negative 3. So there we go. There's my two lines, right? And if I want to find the intersection, right, like that. So the graphing method sometimes works pretty well. It has a visual representation of the problem, which is nice. Right, I can see, let's see, actually, which one's my green line? My green line was this one. And my naranja line is that one. So one of the nice things is I can actually see that this equation is bigger than the orange line all the way up to 10, where they're the same, and it's less than the orange line after that. Sometimes having a graph helps me intuit what is going on in the context of the problem. So, last question. I'm going to cruise through this one. Ready? I've got some facts. Let's figure out our variables here. Write this down on your paper. You didn't have enough room on your paper, you're saying? Oh, okay. Well, what's up? So it is possible. Sometimes the these types of problems, we might try to end up with friendly answers. And you're right, through an amount of guess and checking, we'd be able to figure it out, especially because these end up being whole numbers, right? Because it's I can't sell half of a candle to someone, right? So it sometimes is possible to do guess and check. But what we want you to learn is a strategy that will get you to the solution even if the answers were nearly impossible to guess. Okay, so here we go. Notice the question. To figure out my variables, it says how many of each type of candle did you sell? So my variables are usually going to be the question that's being asked. So I've got everyone's writing this down right now if they didn't get this right. And if they got it right by guessing, they're still writing it down because they need to learn the strategy, not just guessing. So I'm going to say X is the how many is a number question. So number of, and it looks like I sell small and large candles. So let's let X equal the number of small candles. Yeah? And we'll let Y equal the number of so, right, we have the answer, but do you know how to get there? You know how to get there. So here we go. So let's write our equations. In this case, this is a system of equations. There's going to be multiple equations that I'm writing. So it says this. You collect $144. Now this is about money. Notice I've got some other facts about money here, and here. How could I combine those blue facts to write an equation? That's the total amount of money I earned. Oh. Yeah. Because notice this looks like the larger candle. This looks like the smaller candle based on those dimensions. So yeah, so I could have, there are $6 per small candle. Okay, so if I take $4 and multiply by the number of small candles, this term represents the amount of money I earned selling just the small candles. If I take $6 and multiply by the number of large candles, this term alone represents the amount of money I earned from just the large candle sales. And if I add those two together, that would equal the total money I made. Okay. Here's another fact. It says I sold a total of 28 candles. How could I represent that? So it's not going to be about money, so I don't care about any of those. The total number of candles I made is the combination of small and large candles I sold, right? So that's just going to be, yeah, X plus Y. I like it. All right. So X plus Y equals 28. And 4X plus 6Y equals 144. Let's, now what I need to do to solve this is graph these things. Let's rewrite this purple equation in Y equals MX plus B. So I'll subtract X from both sides, and I would have Y equals negative X plus 28. And so that's a Y-intercept at 28, and it's going down 1 over 1, down 1 over 1, down 1 over 1. It's actually going to intercept all the way over here at 28. If I gave myself some points that are further away from each other, I can usually get a better, more accurate line. And notice I'm only drawing this in the first quadrant because it's difficult to sell a negative number of candles. It's like you showed up at someone's house and were like, hey, or actually this is a craft fair, and you're like, hey, I'm selling small and large candles here, and then someone's like, I'll sell you this small candle, $4. And it's like, no, I'm trying to sell candles. I don't want to buy candles. I'm trying to make money. I've got these extra candles I'm trying to get rid of. I don't want more, right? So yeah, I'm not selling negative quantities of candles. Let's see, can we figure out this other equation? 4x plus 6y equals 144. Let's try to write this in slope-intercept form. Any ideas, folks? Subtract 4x from both sides. I'm trying to get y by itself. So 6y equals negative 4x plus 144. Now what do you think? Divide both sides in their entirety by 6. Yep, that's fine. That's fine. And so I'll have y equals 4 and 6 are both divisible by 3. I'll call that negative 2/3 x. And 144 divided by 6, is that going to be 24? 24. Here's my blue equation. So the y-intercept is 24, so I'm going to start at 24, right? And the slope is negative 2/3. Even if I used negative 4/6, it would actually still work for me. Down 2 over 3, down 2 over 3, down 2 over 3. And it looks like I found the intersection, but looks something like this. Be that graph. And so I graphed it, and I can find that the solution occurs right here. It appears to be 12, 16. You guys agree? That appears to be the intersection. Yeah. 12, 16. And so now I can answer the problem. What does 12 mean in terms of this problem? Is 12 the number of hours that a candle will burn? Is 16 the number of craft fairs I've been to this month? What do these represent? Yeah, 12 is X. X is the number of small candles. So I just combine those as a sentence. You sold 12 small candles and 16 large candles. Nice. All right, so I just combine that and I write my sentence answer. Thanks for watching, Internet friends. Adios.